Hello everyone, I'm Adam. In this problem, for a given space curve r of t, what we want to do is find the tangential and normal components of the acceleration vector at the given time t equal to 1. Now to help us out, we have a theorem from our section that says that for r of t being a position vector for some smooth curve c, where a unit normal vector n of t exists, then we can compute our tangential components and normal components using these formulas here. So getting started, if we want to try to compute, say, the tangential component, we can maybe look at the first part, and if we took the derivative with respect to t of the magnitude of v, that would give us that. So that's where we'll start. So let's take a look at v, or our velocity vector. So v of t, which is equal to r prime of t, which is going to give us the vector. So the derivative with respect to t will have just, say, I plus 2j minus 3k. And say taking a look at the magnitude of v equal to the square root of the sum of squares, right, of our components, 1 squared plus 2 squared plus negative 3 squared is going to give us a square root of 14. Okay? Now, what we could do is jump right into, like we said, using that first formula. So if we took the derivative of our magnitude of v, we have the derivative of a constant, and we just get 0. And so we could think that the tangential component of our acceleration vector is just 0. But there's a problem kind of lurking in the background. So if we take a look at our theorem, one of the conditions for these formulas to be valid is this, that our unit normal vector has to exist. And we can kind of see a problem with that kind of emerging when we look at what we got for our velocity vector here, in the fact that everything remaining was constant in terms of t. So let's take a look again at what n is and kind of talk about that, or how it's defined. So our unit normal vector is equal to the derivative with respect to t of our tangent vector divided by the magnitude of t prime of t, provided that t prime of t is not equal to 0, which makes sense, because if t prime of t was equal to 0, the magnitude would be equal to 0, and we'd be dividing by 0 and get something undefined. But that's the thing that we have to take a look at. If we take a look at what t is, and remember that, so the tangent vector is equal to r prime of t divided by the magnitude of r prime of t, which is equal to r prime of t is just the velocity, v of t, divided by the magnitude of the velocity, v of t. All right? So taking a look at what we have with that from our velocity here, so our tangent vector can be written as dividing by the constant all the way through. We would have, say, 1 over the constant or magnitude of v, square root of 14i, plus 2 over the square root of 14j, and minus 3 over square root of 14k. So now what's going to happen if we take the derivative of this? What is t prime of t? Well, as we said, everything is constant in terms of t. So this is just going to be, say, 0, or the 0 vector, which is what we mean up here when we say t prime of t not equal to 0, meaning not equal to the 0 vector. So we have t prime of t equal to 0. So what does that tell us? Well, our unit normal vector is undefined. So that kind of throws kind of a monkey wrench into everything. So now the tangential component and normal components are also going to be undefined because we don't have this unit normal vector. So we actually don't have too much more work to do from here. So our tangential component, we're just going to say is undefined, as well as our normal component is undefined. So there we have Now, the important thing here is to make sure that you're checking the conditions of a theorem before you jump into using it. Thank you very much.